Okay, Assalamualaikum and very good morning to everyone. Okay, so today if we continue our topic, which is process synchronizations. Okay, in this topic, you will learn about how the cooperating process will affect or be affected by other process executing in the system. So cooperating process can be either directly share a logical address space, either the code or the data, or it can be allowed to share data only through the files or messages. So in the previous chapters, you will learn how to achieve the use of threads. Okay, you will learn about the threads and the multi-threadings, how it being the concept, and also how they is being being operate. So since they have a thread and the multi-threads which is running concurrently, so the concurrent access has a possibility on the concurrent access to shared data, which can result in data inconsistency. Okay, so therefore in this chapter, you will discuss about the various mechanisms in order to ensure the orderly executions of the cooperating process that share the logical address space so that the data consistency is maintained. Okay, so kita akan maintain, kita tengok kalau dalam proses kita akan ada proses yang that concurrent process or we call a cooperating process. Okay, some threads and we have a multi-threads, okay, that running concurrently. So how they share the data, how they share the codes, okay, at the same time, they can run at the same time the data that can be accessed both process and that access concurrently can be maintained the consistency rate. So this is the object, the outline of this topic. Okay. Some of the solutions are in the hardware solution and some of them are in the software solutions. So we have to look the concept saja, yang topik subjek ni dia lebih kepada konsep. It's very important when you have a multiprocessor. So kita akan tengok kalau kita single processor, they are able to do the threads and the multi-threadings. So macam mana dia maintain dia punya data consistency dia, and then dalam masa yang sama kita akan tengok ada juga some of this concept is being used, okay, in the multiprocessing. So this is the objectives, okay, where you will be able to describe the critical section problems and illustrate the race conditions, okay, and you can see that the different solutions for the hardware solutions or the software solutions in order to maintain the synchronizations of the data or the process synchronization. So they demonstrate how the Mutex logs, Semaphores, monitors, and the condition variables can be used in order to solve the critical section problems, okay, and evaluate the tools that solve the critical section problems either in the low, moderate, and high contention scenarios. Okay. Okay, so previously we already discussed about the process can execute concurrently or in parallel. Okay, so kita dah tahu dah processes able dalam operating system, the process is able to can execute concurrently and it can be worked in the parallel. So this means one process may only partially complete execution before another process is being scheduled. In fact, kalau ada process, it can be interrupted before another process is being scheduled. Okay, in fact, okay, a process may be interrupted at any point in its instruction stream, and the processing core may be assigned to execute instruction of another process. Okay, additionally, okay, we already introduced to you to execute instruction of another process. Introduce a parallel executions in which two instruction streams, okay, execute simultaneously on the separate processing core. So dalam chapter ni kita akan explain macam mana concurrent ataupun parallel execution can contribute in issues that involve in the integrity of data shared by the several process. So guys, sini kita akan nampak ada beberapa isu yang perlu diberi perhatian, okay, of the programmer, especially the designers for the operating system when you run a process that running in the concurrently. So there are several issues that need to be considered. Okay. Alright. So in these issues, okay, kita akan discuss about dia punya, okay, kita akan discuss dia punya isu dia ialah, okay, kita akan tengok we have a different process, okay. For example, we have a process 0, okay, and process 1 creating the child process using the fork function ataupun kita panggil the fork system call. So namanya P0 dengan P1 ni dia ada dia punya child process, maksudnya dia ada sub process that running. So apa yang berlaku ialah, okay, apa yang berlaku ialah the race conditions akan berlaku, okay, on the kernel variables, okay, di mana dia akan represent the next available process identifier. Okay, kita tahu setiap proses ada proses identifier dia sendiri. So kalau kita ada child, fork child, maknanya dia ada sub process. So dia akan create another sub process of ID, sub process ID yang sama, tapi dia akan tahu this is belong to the fork child. Child dia 2615. Okay, so P1 dia ada dia punya ni. Okay, ataupun dia sharing the same fork child. So apa yang berlaku ialah apabila dia P0 dan P1 dia running secara concurrently dan dia akan mengakses benda yang sama, maka dia akan berlaku we call as a race condition. Okay. Alright. So in the race conditions, okay, the race condition is happens where the situation where the several process access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which the access takes place. So dia akan ada berlaku race conditions, okay, berlaku perebutan, okay, berlumba-lumba. Dia nakkan accessing the data ataupun the resources. Contohnya dia nakkan input device ataupun dia nak output device, okay, the same forks, correct function yang tadi tu dia perlukan access pada proses pada certain data. Apabila berlaku perebutan di sini, dia akan dapati data yang diterima oleh kedua-dua tu adalah data yang inconsistent, data yang tidak boleh dipakai lah. Kalau kita dalam technical dia panggil sebagai garbage data. So dia kata as a garbage data lah. Okay. So to guard against the race condition, kita kena ensure that only one process at a time can be manipulating the variables. Okay. Kita kena pastikan dalam operating system kena pastikan benda ni. Apabila berlaku race conditions, kita make sure that only process dalam satu masa yang akan do some manipulations, okay, can access the data, and then to make sure they guarantee the process must be synchronized in the some way. Okay, right. So therefore, the situation such as the just as described tadi akan frequently operate as a different parts of the system manipulate resources. Ini selalu berlaku, bukan sahaja data, dia akan berlaku race condition dari segi resources. Okay, contohnya dua sistem nak access, dua proses nak access memori pada masa yang sama. So macam mana operating system may decide which process need to be accessed that particular memory dalam pada masa tersebut. So ini akan berlaku apabila dia berlaku cooperating ataupun berlaku dalam concurrently ataupun parallel. Kalau dia berlaku in the sequential, dia tak akan berlaku lah. Dia tak akan berlaku race condition. Okay, so furthermore dalam chapter ni kita akan tengok the growing the importance of multi-core system has brought an increased emphasis on developing multi-threaded application. So dalam ni kita akan tengok bukan sahaja single processor, kita akan tengok juga di dalam a multi-core. Multi-core maknanya you have more than one processes, okay, that running. Dan macam mana dia akan create, okay, macam mana dia boleh develop atau create the multi-threaded application. In such application, several threads which are quite possibly sharing data can be running in parallel on the different processing core. Okay, it's been clearly that we want to change the result from the such activity not to interfere with another process. Okay, kalau kita buat proses, kalau buat changes the result tu, kita nak pastikan kita nak kena pastikan aktiviti tu tak ada mengganggu atau mengganggu gugat proses yang lain. So that's why because of this importance of this issue, we devote have a major portions to have a chapter on the process synchronization and coordination among cooperating process. That's why topik ni antara topik penting dalam principle of operating system, di mana how your process can be synchronized. Okay, how your process can be synchronized. Okay, when you have a multiple process running in a multiprocessor. Alright, so each process, okay, so we have a call. Dalam ni, okay, kita akan tengok issue dulu and how we solve it. Okay, so the first thing, we begin the consideration of process synchronization by discussing the so-called critical section problems. Okay, dalam critical section problems ni, okay, we consider a system consisting of n process. Okay, kita assume saja, okay, dalam satu operating system kita ada n process. Kita tak tahu berapa banyak. Okay, dia bergantung kepada user. Okay, how many process, bergantung pada komputer, dan juga dia bergantung kepada user itu sendiri, berapa banyak program dia buka dalam masa yang sama. Then each process has a segment code, or we call as a critical section. Setiap proses ni, okay, kita consider dia ada n proses. So setiap proses dia ada critical section dia. Okay, critical section ni macam the segment of code lah. Okay, so in which process ni may be changing. Okay, bila dia ada segment of code ni, dia akan menyebabkan ada perubahan pada variable dia. Kita update the table, writing the file and so on. Banyak. Setiap section, critical section ni dia ada activity dia. Okay, antaranya ialah activity dia ialah changes dia punya variable, you update dia punya table, okay, writing the file and then banyak lagi. Okay, kalau macam you access your system tu dengan database, so you akan write the file tu akan write into database, save dalam database, lepas tu ataupun you nak buka file daripada database. Okay, so the important features of the system is that when the one process is executing in the critical sections, there's no other process is allowed to execute in its critical section. So dalam case ini, apa yang kita buat ialah kita kena pastikan, okay, mana-mana proses yang tengah run dia punya critical section, so proses lain tidak dibenarkan, okay, dia tak benarkan execute dia punya critical section. Okay, there is no two processes, okay, are executing in their protocol that the processes can use to cooperate. So each process must request permission to enter its critical section. So untuk mengingatkan ini, apa kita buat? Setiap proses yang nakkan buat critical section, dia kena minta permission. Okay, permission in order to enter, masuk ke dalam entry critical section tadi. Okay, so bila dia minta critical sections, so how kita implement dia, kita akan letak satu section of code, implement this by request the entry section, macam function lah, kita letak satu entry function, lepas tu followed by critical section with the exit section and also the reminder section. So dia ada 3 benda. So dalam setiap proses yang masuk critical section tu, okay, dia ada 3 benda. So dia kena ada entry section, okay, lepas tu dia ada exit section, okay, and then dia ada reminder section. So critical section problem ni kita dah didesignkan as a protocol protocol rules, okay, di mana processes yang cooperate processes, okay, must follow this critical section problems. Okay, dia akan mesti, maknanya kalau setiap proses, satu proses dah masuk critical section, another proses tak boleh run or execute dia punya critical section. So setiap proses nak buat critical section kena ada permission. Okay, so bila dia ada permission, dia kena ada entry section, kena ada exit section, and also dia kena ada reminder section. So the general structure of the typical process, okay, dia akan tunjuk lah. Okay, you boleh tengok dalam buku. Okay, so the entry section and the exit section are enclosed in the boxes to highlight the importance of the segment. So kat sini. So this is general structure of the process. So they must do. So this is entry sections, okay, and you have a critical section, and then you have exit section and the reminder section. So ini dia punya algorithm lah. Okay. Right. So apa yang apa yang diperlukan for solution to critical section problem ni ada 3 benda. Okay, pertama adalah dari segi mutual exclusion. Okay, mutual exclusion adalah di mana if process is executing, any process is executing in its critical section, there's no other process can be executing in their critical section. Kalau dia tengok ada proses yang tengah run dia punya critical section, so proses lain yang nak run juga critical section kena tunggu. Okay, alright. So the progress, okay, if no process is executing in its critical section and there exist some processes that wish to enter the critical section, then the selection of the process that will enter the critical section next cannot be postponed indefinitely. So dalam syarat yang kedua dalam critical section problem, we have a progress. So progress ni dia punya syarat dia ialah kalau tak ada proses yang execute dia punya critical section dan some process dia dah request, okay, dia nak request to enter dia punya critical section, only those process that not executed in the reminder section can participate in decide which process will enter its critical section next. And this selection cannot be postponed indefinitely. Dah tak boleh postpone dah. So progress, okay. So bila tak ada proses yang executed critical section, okay, and ada some proses-proses yang sedang yang nakkan masuk critical section ni, okay, so apa yang OS akan buat selection ialah proses mana yang dia akan membuat pemilihan proses mana yang akan masuk ke dalam critical section dah tak boleh postpone dah. So dia tak ada postpone dah. Dia tak ada postpone dah. Dia terus progress masuk Okay. Dan yang ketiga ialah bounded waiting. So bounded waiting is the bound, okay, that must exist on the number of times that the other process. Okay, bounded waiting, there exists a bound or limit, okay, on the number of items that process are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is made granted. So the bounded waiting ni must be exist, bound ataupun limit. The bound tu macam limit lah. Kita akan limit berapa banyak number of items, number of times of the process can be allowed to enter the critical section after a process has. Dia akan kira selepas proses tu dah request for the critical, dia dah masuk ke dalam request for to enter the critical section dan before the process can be granted dia punya requests. Okay, kita assume each process ni they execute non-zero speed. However, we can make no assumption concerning, okay, the relative speed of the end processes. Okay, at a given point in time, the many kernel mode process may be active in the operating system. So as a result, the code implementing an operating system kernel is subject to several possible race conditions. So akan berlaku. Okay, so kita continue okay, this lecture, okay, with the interrupt-based solutions. Okay, so previously kita tahu interrupt memang dah ada dalam operating system, and operating system is a part of interrupt driver. So, apa yang berlaku dalam interrupt-based solution ni ialah isu yang proses tadi ialah bila proses masuk the critical entry sections, okay, kita dah tahu dia gunakan mutual exclusion punya syarat kan. So dia bila menggunakan mutual exclusion, bila proses dah masuk critical section, dah entry dah masuk entry sections, dia punya interrupt will be disabled sebab only one process can execute or can execute dia punya critical section. So proses lain tak boleh masuk, tak boleh enter the critical section. So bila dah dia exit, proses tu dah buat critical section semua, bila dia dah masuk sampai exit and section, baru interrupts will be enabled. So adakah itu akan solve the problem? Okay, actually no, because apa yang berlaku ialah ia akan apabila ialah dia punya critical section tu, code tu run for an hours, more than 1 hours. Okay, ni biasanya ia berlaku apabila you have a poor designs of your punya coding lah. Okay, so if the critical sections, okay, code ni run for more than 1 hours. Okay, ni proses lain tengah queue ni, proses lain pun nak run dia punya critical section problems. So critical section, so apa yang berlaku ialah bila certain proses tu, bila pakai interrupt base ni, bila critical section tu, proses tu dah enter the critical sections, interrupt automatic disable. Hanya dia akan enable balik bila proses tu dah habis. Okay, the critical section dah masuk exit section, baru interrupt. Okay, proses lain boleh interrupt dan boleh ni. Tapi kita bayangkan satu proses tu, kalau dia punya critical section tu run more than hours, more than 1 hours, several hours. So apa yang berlaku ialah it's not solve the problems. Okay, dia akan menyebabkan berlaku proses starvation. Okay, ataupun we call a process starve, okay, kelaparan. Okay, so because dia tak boleh enter dia punya critical, tak boleh enter dia punya, tak boleh execute dia punya critical sections. Dan apa yang juga yang berlaku sebabkan ni, sekarang ni kita punya teknologi CPU, walaupun dia single processor, tapi dia boleh have illogically, okay, physically one processor, tapi logically kadang-kadang they have two more of CPUs. So what happens? So you have not fully utilized you punya CPU. That's the problems. Okay, some process will starve, okay, to enter the critical section, tapi dia tak boleh masuk sebab syarat, kita ikut syarat yang pertama tadi adalah menggunakan critical section, yang mana kalau dah berlaku critical section, proses lain tak boleh execute dia punya critical section. Tapi untuk one particular processor, how about we have more than 2 processors? Okay, we have a 2 CPUs running, we have 2 CPUs. So that the issue are coming in lah. Okay, so low CPU utilization, okay, you tak low CPU utilization, banyak menyebabkan proses starve, okay, proses starving, okay, bila you pakai interrupt based solution. Okay, bukan kata interrupt ni tak boleh pakai, boleh, okay, cumanya dia akan create beberapa isu lah. Antaranya isu sebab setiap proses bila masuk entry section, disable dia akan interrupt. Dan hanya boleh dia interrupt, proses lain boleh interrupt hanya bila proses tu dah left the critical section tadi. So nak kena tunggulah. So berapa lama nak tunggu tu? Dan itu satu isu dia yang kena solve. Okay, alright. So how we do a solution? So solution pertama ialah menggunakan software solution. Okay, alright. So two process solutions ialah dia menggunakan solution pertama adalah dia guna process solution, iaitu assume we have a load and store machine language instruction which is atomic. atomic tu 1, satu. Okay, and cannot be interrupted. So the two process share one variable. Okay, contohnya INTG turn tu. Okay, the variable turn will indicate whose turn it is to enter the critical section. So solution pertama dia ialah dia solve dengan menggunakan software solution, iaitu gunakan load and store. Load and store ni kita you dah belajar masa you dah belajar load and store ni dalam machine language. Dalam machine language kita ada satu function which is load and store, which is specific instructions, okay, that cannot be interrupt. So kalau ada load and store ni, so processor ni dah tahu dah, okay, kita tak boleh interrupt. Okay, so and these two machine function ni kita akan share gunakan satu variable dipanggil turn. Turn ni akan memberitahu or indicate kita siapa the next process yang akan take or enter to the critical section. Okay, so this is the punya algorithm lah. Okay, right. Okay, so okay, so kita kena correctness of the software solution. The mutual, okay, exclusion is preserved. Okay, so maknanya syarat yang pertama tadi mutual exclusion, there's no process only one. Kalau ada proses yang enter for critical section, proses lain tak boleh execute dia punya critical section. Okay, so kita dah preserve dah mutual exclusion yang pertama, di mana kita pastikan bila mana proses yang enter critical section dia akan turn, okay, the next process. Okay, so macam mana buat the progress requirement? Progress requirement tadi, kalau tak ada proses yang exist dekat dalam critical section, so dia boleh masuk kan. Dan macam mana pula dengan bounded waiting requirement tadi? Dia tak solve lagi. So maknanya interrupt based solution yang kita bagi tadi, dia hanya boleh solve the mutual exclusion saja, tapi dia tak solve the progress requirement dan juga bounded waiting punya syarat. Okay, so that's why we come up with the one solution, okay, which is the Peterson's solution. So Peterson solution ni, they use two process solution. This is a classic software based solution to the critical section that dia panggil sebagai Peterson solution. Okay, so because of the way of modern computer architecture perform the basic machine language such as load and store, then there's no guarantee that Peterson solution ni will work correctly on the modern punya computer architecture. Okay, macam modern computer architecture contohnya pakai object oriented, okay, multi-threading, so it's not guaranteed. So however, we present the solution because they provide a good algorithmic descriptions of how to solving the critical section problem and illustrate some of the complexity involved in designing software that address the requirement of mutual exclusion, progress and the bounded waiting. So walaupun Peterson solutions ni is a classic software solution, okay, tapi tak menjamin ianya boleh digunakan dalam modern computer architecture. Tapi oleh kerana kenapa kita discuss juga this kind of solutions, kerana dia provide a good descriptions dari segi algorithm dia dalam nak solve critical section problem lah. Okay, di mana dia boleh address bila dia design the software Peterson solution ni, dia boleh address requirement untuk mutual exclusion, the progress dan juga the bounded waiting. Okay, so dalam Peterson solution ni, dia suggest two process solution. And then we have the load and store machine language, which will be instruction that will be atomic and that cannot be interrupted. So the two process share the two variables, okay, which is int turn dan juga boolean flag. So variable turn ni akan indicate proses yang mana yang akan the next process yang akan enter the critical section, and the flag array ni akan indicate which process is ready to enter the critical section. So dia apply lah, okay, so apply the mutual exclusion. So dia take turn, okay, untuk proses Mutex proses yang akan enter the critical section, dan dia akan bagi tahu array indicate proses mana yang akan ready untuk enter the critical section. So this is the so Peterson restricted to process the alternate execution between the critical section and the remainder section. So the process are numbered, okay, for example P0 and P1, okay. So for convenience, we're representing we use Pj to denote another process that use J equals to 1 minus I. So Peterson solutions provide two process that to share data item iaitu entity turn dan juga boolean flag. So dalam the variable turn ni, macam kita cakap tadi, indicate whose turn to be entered the critical section. Okay, then the process, okay, if the turn equals to I, then the process akan allowed to execute the critical section. So the flag array tadi akan used to indicate the process that is to be ready to enter its critical section. So kalau the flag to true, so this value will indicate the PI is ready to enter the critical section. Okay. Okay, to enter the critical section, process ni akan set as a flag I to be true and then set turn to be value J. So kita nak bezakan so there why they assert that if the other process wish to enter the critical section, it can do so. If both process try to enter at the same time, the turn will be set to both I and J roughly at the same time. Okay, dia guna and kan. So only one of these assignment will last, okay, and the order will be occur but will be overwritten immediately. So the eventual value of turn determines which of the two process is allowed to enter its critical section first. So now kita boleh buktikan, okay, we can prove that this solution is correct. Okay, di mana so Peterson solutions ni provide the three requirement. Okay, critical section requirement. Met the critical section punya requirement lah. First, the mutual exclusion is preserved. Okay, di mana the process enter CS only if the false or turn into I. Okay. And the progress requirement is satisfied, and the bounded waiting requirement also is met. Okay. Okay. So although useful, okay, walaupun Peterson solutions ni, okay, can demonstrate, okay, a good algorithms, okay, but it cannot guarantee to work in the modern architecture with the current architecture because they have to improve the performance, the processes, or the compiler may be reorder operations that have no dependency. So understanding why it works not work is useful for better understanding the race conditions. Okay, for single threaded this is okay as the result will always be the same. So dalam Peterson solutions ni, okay, untuk classic punya boleh. Okay, classic punya architecture boleh. Okay, for single threads it can be happens. Okay, it's okay. For alright, we have good result, but with the current, okay, modern architecture such as a multi-threading, okay, we have a multiprocessing, symmetric multiprocessing, lepas tu kita ada asymmetric multiprocessing, okay, so it not produce inconsistent or unexpected results. Okay, so that's why the Peterson solutions ni only can classify as a classic software solutions. Okay, so we continue our videos. Okay, so previously we discussed about the software-based solutions to the critical section problems. However, we mentioned that software-based solutions such as like Peterson's solutions is not guaranteed to work on the modern architecture. So in this topic, in these slides, we will discuss about how we explore several more solutions to the critical section problem using the technique ranging from the hardware to software-based API, which is available to both kernel developers and also application programmers. So all these solutions are based on the premise of locking, which means that they protect the critical regions through the use of lock. As we shall see, the designs of such lock can be quite sophisticated lah. As we know, critical section problem could be solved in the simple single processor environment. So it can be solved only in the single processor environment, which can prevent interrupts from occurring while a shared variables was being modified. So kita tak ada isu kalau kita run critical section problem, takkan ada can be solved apabila we have a single processor or uniprocessor, because kita boleh disable the interrupts. Untuk disable or prevent the interrupts from occurring while when sub-process ataupun the sub-process tu share the variables ataupun variable tu sedang dimodified. In this way, we could be sure that the current sequence of the instruction will be allowed to execute in order without preemption. So kalau code tak ada isu lah. So run code yang running tak perlu ada berlaku force untuk CPU, untuk force untuk paksa lepaskan processor. Kerana tak perlu ada without preemption lah. Without any preemptions, there's no other instruction akan run, so no unexpected modification could be made to shared variables. So this is the open approach taken by the non-preemptive kernel. Unfortunately, this solution is not feasible in a multiprocessor environment. So untuk Peterson solution sesuai untuk single processor. Tapi kalau untuk multiprocessor environments, is not being feasible. When you disabling interrupt on a multiprocessor, it can be time consuming. Because when you we pass the message to all the processors, this message passing will be delayed entry into each critical section, and the system will be efficiency decrease. Dia akan menyebabkan your system akan too inefficient on the multiprocessor system. And then menyebabkan you punya operating system tak boleh broadly scalable. Kamu tak boleh expand awak punya enhance awak punya operating system secara scalable. Also consider the effect of the system clock if the clock is kept updated by the interrupt. So in the many modern computer system, therefore they provide a special hardware. Alright, so that's why they have a special hardware support. Which is hardware that will allow the user to test and modify the content of the words or to swap the contents of the two words secara atomically. I say secara atomically di mana only one interruptible units. So we can use this special instruction to solve the critical section problem in the relatively simple manner. Daripada kita discuss specific instruction for one specific machine, kita akan abstract the main concept behind the types of instruction by describing test and set. Dia ada dalam synchronization hardware ni, dia akan introduce dua benda. Satu ialah hardware instructions, support dengan hardware instruction. Then dia akan buat two functions, secara atomically, okay, iaitu test and set and compare and the swap instruction. Okay. Okay, so dalam hardware instructions ni, they use a special hardware instruction yang saya cakap tadi lah. Either guna test and modify the content of words or to swap the contents of two words secara atomically or interruptedly. So dia ada dua instruction, satu test and set instruction, satu compare and swap instruction. So test and set instruction ni, okay, normally dia akan execute secara automatically, okay, and then dia akan execute simultaneously. Okay. Kalau dia multiprocessor, dia boleh run secara each in different CPU lah. Okay, then will be execute sequentially in the some arbitrary order. So dia boleh secara sequentially ataupun dia boleh run in a different CPU. If the machine support the test and set instruction, then we can implement the mutual exclusion by declaring the boolean variable log and initialize to initialize false. Okay, so that is test and set instruction. Okay, untuk compare and swap instruction, okay, dia kontra dengan test and set tadi, di mana dia operate on 3 operands. Okay, di mana the operand value is set to new value only if the, okay, so this is the test set instructions. Okay, yang saya terangkan tadi. So the boolean test instruction dia ada boolean and also the target, and normally this test set instruction execute secara automatically and they return the original value of the pass parameter. Again, set the value parameter to the true. Okay. This is the solution for test and set. Okay, this is a compare and swap yang saya cakap tadi, di mana di dalam compare ini dia ada 3 operands. Okay, di mana the operand is a set to the new values. Okay, kita akan set dia as a new values. Only if the expression the value equals to expected. Bila value and expected ni betul, true, baru dia akan set the new value. Then regardless the compare the swap function always return the original value. Dia akan return balik the original value of the variable value. Okay, like the test and session, they compare and swap. Okay, right. So yang ini pun dia run secara automatically. Dia return the original values and dia akan set the values. Okay, dia set the new values bila value tu sama dengan expected lah. Okay. Alright, so bila dua function ni run secara automatically, the mutual exclusion can be provided as follows. They have a variable log. So okay, dia ada variable log. Okay, so dia ada variable log, and then dia akan log benda tu. Okay. Okay, so variable log. So dalam variable log, which you can provide as a global variable log is declared and initial to 0. So the first process invoke the compare and swap will set log to 1 and it will then enter a critical section because the original value of log was equal to the expected value of 0. So subsequent call to compare and swap function will not succeed because the log now is not equal to the expected value of 0. So when process exit the critical section, then the set log back will be to 0 balik. So which allow another process to enter its critical section. So macam yang proses tadi lah, there has a mutual exclusion dengan compare. Okay, walaupun solution ni, okay, dia satisfy the mutual exclusion requirement, but they do not satisfy the bounded waiting requirement. Di mana dia akan present, di mana, okay, so we can see that dalam ni, okay, data structure ni, okay, we build another algorithm with the set instruction that satisfy, okay, instruction critical powers, okay, okay. So apa yang berlaku ialah the mutual exclusion is met, okay, and then tapi alright, to prove the progress is met, kita nampak argument presented in the mutual exclusion also applied, okay, di mana dia akan to prove the bounded waiting. We know that when the process leave the critical section, then they akan scan the array waiting in the cyclic ordering. So it designed the first process in this ordering, that is entry section, which is next one to enter the critical section. So any process waiting to enter is critical section will, so that with the n-1 will be turned. So okay, kita akan nampak implementation atomic test set ni dengan and the compare swap ni instruction dalam implementation nanti. Okay. Alright, so dalam locking ni, so dia hanya bila dia enter critical sections, okay, dia akan equals to set 1. Tapi kalau the left, okay, maknanya dia akan set back into a 0 lah. So typically instructions such as compare, swap are used as a building block for other synchronization tools. So another tool is we call atomic variable, di mana this provide the atomic uninterrupted updates on the basic data type, okay, such as yang ni lah okay. So atomic variable kita ada variables kat sini, okay, yang dia akan compare and swap, and then temporarily dia akan return balik lah, okay, the variables. Okay. Alright, so yang tadi dia bahagian log. So in the hardware-based solution to the this problem, kita nampak macam complicated, okay, inaccessible to application programmers. Okay, instead of operating system designers build software tools to solve the critical section problems, the simplest of these two is the Mutex logs. Okay, kita tambah macam log tu nampak complicated kan? Kita ada test set, compare, lepas tu ada compare and swap instruction pula. So kita instead kita biar operating system designer yang fikir software tools untuk solve critical section problem, kita bagi make a simple one tools yang kita panggil sebagai the Mutex logs. Okay, Mutex, in fact the terms of Mutex in the short of for the mutual exclusion. Okay, Mutex tu maksudnya mutual is a short form for the mutual exclusions, okay. Okay, dan dia tambah dengan log. So we use the Mutex logs, okay, to protect the critical region and this to prevent the risk conditions. Okay, so kita pakai the Mutex logs. Okay, so dalam Mutex log ni, okay, dia ada boolean variables, okay, that indicate if the log is available or not. So the Mutex ni akan indicate sama ada the log tu is available ataupun tidak. Kalau log tu available, okay, if the log is available, then they have an acquire a function, ada acquire function ada acquire function of logs, okay, and then they release the log function and release functions, okay, untuk release the log. Okay, release function ni untuk release the log, acquire ialah untuk request a log, and then acquire the acquire and the release function ni dia akan call okay, in atomically, okay, dalam retro system call lah. Okay, normally dia akan implement dalam bentuk hardware atomic instructions such as a compare and sort tadi lah. Okay. Okay. So, tapi mutex lock ni disadvantage dia ialah dia require of busy waiting, di mana while process is in critical section, any other process that try to enter its critical section must loop continuously in a call to acquire function. So satu masalah dia, mutex lock ni nampak macam simple, okay, tetapi apa isu dia ialah dia akan menyebabkan proses akan keep busy waiting. Okay, dia akan menyebabkan satu continual looping. Okay, okay, continual looping. It can create a continual looping di mana dia akan keep acquire for the lock. Okay, alright. So therefore this mutex locks, this type of mutex lock kita dia panggil sebagai spin lock, kerana the process will spin while waiting for the lock to become available. Spin lock. Kenapa dia panggil spin lock instead of mutex lock? Because the another process akan keep spinning, busy waiting, okay, call for acquire functions in order to request for the lock lah, supaya dia boleh masuk critical section. Okay, to make sure there will be available word. So spin lock ni have an advantages. Okay, however, there's no contact switch. Okay, it's required when the process must wait on a lock, and contact switch may take considerable time. Thus, when lock are expected to be held for a short time, spin lock are useful. They are often employed on normally mutex lock ni banyak digunakan dalam multi-processor system where bila one thread to spin on one processor, another thread can perform a critical session in another processor. So itu kebanyakan dalam multi-processing ataupun symmetric multi-processing punya architecture, dia akan menggunakan mutex lock punya konsep lah. Basic konsep, tapi dia ada tambah lain lagi lah. Okay. Okay, this is how the problems, okay, using the mutex lock yang tadi lah. So the acquire lock functions, okay, before they can enter the critical section. So bila dia dah siap dia punya critical section, dia akan do some release the lock functions. So apa yang berlaku ialah yang mana busy waiting ni dia akan keep acquire the lock. Busy waiting tu yang dia continual loops tadi. Okay, dia akan continual loops. Okay, untuk that's what called a spin lock tadi. Alright. Okay, now we go to the semaphores. Okay, semaphores ni hampir sama dengan mutex locks. We use a mutex locks punya concept. Okay, and okay, tapi kita tambah baik lagi dengan more robust. Okay, di mana dia akan menggunakan robust tool that can behave similarly to mutex locks, but can provide more sophisticated way for the process to synchronize dia punya activity. Okay, ni banyak berlaku di dalam multiprocessing lah. Okay, so dalam synchronization tool that provide more sophisticated way, Semaphore ni, okay, enhancement daripada mutex locks, okay, tapi dia provide lebih pada sophisticated way, not like a simple such as like a mutex lock, for the process to synchronize dia punya activity. So dalam Semaphore ni, apa yang dia buat? Dalam Semaphore dia akan introduce a Semaphore as an integer variable, which is apart from the initialization, and is accessed only through two standard atomic operation, which is wait and the signal. So dia ada two indivisible operations, waiting function and also signal function. Okay, so dalam waiting operation, okay, there was original term, okay, di mana okay, untuk test, okay. And signal was originally called V from Vogons, okay, to increments. So waiting dia ada dia punya operation dia sendiri, and okay, so busy, okay. So all the modification dalam to the integer value of the semaphore ni dalam wait ni, and the signal operation must be executed indivisibly. Okay, so maknanya boleh dibagi secara sama rata. That is when the one process modify the semaphore value. Kalau ada one process modify the semaphore value, then another process can simultaneously modify the same semaphore value. So that's why the S in semaphore values ni sangat important. Dalam semaphore dia akan create the some integer variable ni, di mana proses lain boleh guna balik. That kind of semaphores, okay. Dan boleh execute secara concurrently. So, okay. Alright. So in addition, if the case of weight of S, okay, the testing of the integer value S, okay, which is S, so equals or less or equals than 0, as well as its possible modification of S minus and minus, must be executed without interaction. So dia boleh keep continuing doing lah. Okay, tanpa berlaku interruption. Okay, so we can see that this operation can be implemented lah. Okay, dalam macam mana semaphore is being used. Okay, so operating system oftenly distinguish, okay, boleh beza antara counting and the binary semaphore lah. Macam mana operating system boleh bezakan yang mana counting and binary semaphore. Okay, the value of the counting semaphore can range over unrestricted domain. Unrestricted domain, they can be any numbers. Tak ada restricted lah, tak ada restrict dia ada restrict. Tapi untuk value of the binary semaphore, dia ada range dia antara 0 dan 1 sahaja. Okay, so binary semaphore behave similarly to mutex logs. Okay, so mutex, so binary semaphore ni akan sama works on the mutex logs function. In fact, the system do not provide mutex logs. Okay, the binary semaphore can be used instead of providing the mutual exclusion. So in the counting semaphore can be used to control access to a given resource consisting of an infinite for the finite number of instances. So the semaphore is initialized to the number of resources available. Setiap proses wish to use a resource perform a wait operation. So mana proses-proses okay yang run the critical section and wait and require for resources, okay, we can have to go to the wait operation on the semaphore, and when the process release a resources, then it can be perform a signal operation, okay, or incremental count. So when the count the semaphore goes to 0, all resources are being used. So processes which use the resource will block until the count becomes greater than 0. Okay, so we can use the semaphore to solve the various synchronization problems. For example, when we have two concurrent running process. Okay, alright, we have a two concurrent process running, which is a P1, okay, with the statement S1, and P2 with the statement of S2. Okay, suppose we require S2 to be executed only after S1, okay, has completed. So we can implement this scheme readily by let the P1 and the P2 share the common semaphore sync with the initialized to 0. So in the process P1, we insert the statement lah. S1 kita insert the statement signal sync lah with the value signal sync, and then in the P2 kita ada wait sync. So apa yang perubahan pada signal sync ni akan diterima dekat waiting sync. Okay. Okay. So Semaphore, must guarantee that the snow process can execute the wait and the signal on the same semaphore at the same time. Thus, the implementation become the critical section problem where the wait and signal code are placed in the critical section. So they could not have a busy waiting. So dia tak ada problem dah. Macam Mutex, so dia ada busy waiting kan. So dia akan berlaku loop spin lock. Tapi yang ini dia tak akan have busy waiting in hanya berlaku busy waiting di dalam critical section during the implementations of the code. Dan buat implementation dia code mesti very short. Okay, dia tak boleh terlalu panjang dan dia mesti very short and because they nak less the computation time. So they have make sure that the little busy waiting execution rarely occupied. Okay, so this is a critical in the single process environment. We can solve the simply inhibiting interrupt during the time and the wait and the signal operation executing. This scheme work in the single processor environment because once interrupts are inhibited, instruction from the different process cannot be interleaved. Okay, only the current running process execute until interrupts are re-enabled and the scheduler can regain the control. So dia tak ada issue lah kalau in the single. Dalam multiprocessor environment, interrupt must be disabled on every processor. So otherwise, instruction from different process running a different processor may be interleaved in some arbitrary way. So bila dalam single processor environment, kita tak ada issue dalam semaphore ni sebab they can solve inhibiting the interrupts, during the time wait and signal operations lah. Tapi dalam multiprocessor, interrupt will be disabled on every processor. So otherwise, instruction from different process that running on the different processor may interleave in some arbitrary way. So therefore, SMP system must provide the alternative locking techniques, such as a compress swap or spin lock to ensure that the wait and the signal are performed secara automatically. So it is important to admit that we have not completely eliminated busy waiting with this definition wait and signal operation. Rather, we have moved busy waiting from the entry section to the critical section of the application program. Furthermore, we have a limited busy waiting to the critical section of the wait and the signal operation, and these sections are short. Thus the critical section is almost never be occupied and busy waiting occurs rarely. Then for only a short time. Akan ada berlaku tapi in very short time. So an entirely the different situation exists with the application program whose critical section may be long. Dia akan berlaku in this situation apabila application tu it takes too long. It takes a minutes or even hours to be occupied or to be execution. So nanti kalau bergantung juga kepada program. Kalau program tu terlalu panjang ataupun it takes too long to be executed, then busy waiting akan extremely inefficient lah. So each answer is associated with a queue. So to operation, the block is where the place the process invoke the operation on the operate waiting queue, and wake up when they remove one of process in the waiting queue and place in the ready queue. This is how they implement. So even though the semaphores normally implements in the multi-processor environments. However, this semaphores does not eliminate the critical section problems, but it can make the critical sections more efficiently, right? Thus, the critical section is almost never occupied, and busy waiting occurs rarely, and then for only a short time. An entire different situation exists with the application program, which critical section may be long or it can be always be occupied. So problems with the semaphores ialah apa yang berlaku ialah semaphores can be incorrect use, okay, in the semaphore operation, and especially on the signal function and the waiting functions. Okay, alright. So they omit the waiting functions in the mutex, and or the signal mutex. They make the example of where they can occur when the semaphore and other synchronization are used incorrectly. Okay, another problem with the semaphore ialah okay, bila kita implement semaphore ni with the waiting queue, we may result two or more process waiting indefinitely for an event that can be caused only by one of the waiting process. So the event in the question is the executions of the signal operation, and when such a state is reached, this we call a deadlock. Okay, deadlock ni kita akan go to the next chapter dalam topik the next chapter yang kita ada dalam satu chapter khusus untuk macam mana nak mengatasi deadlock. Okay, macam mana operating system handle deadlock. Alright, so deadlock and also a starvation. Okay, so bila deadlock berlaku, okay, so contoh, okay, we have a problem, okay, two process P0 and P1 accessing two semaphore S and Q, okay, we access as well. So dua processor, they're waiting, okay, and they access dua semaphore, okay, set S and Q. So apa yang berlaku ialah P0 execute wait S, okay, dia tengah executing waiting, okay, semaphore S, and P1 execute waiting for semaphore Q. So bila P0 execute wait for semaphore Q, it must wait until P1 execute signal Q. So similarly, bila signal P1 execute wait S, it must wait until P0 execute signal S. So this, okay, signal operation cannot be executed because P0 and P1 will have a deadlock. Okay, nanti kita explain lebih dalam how about the deadlock will be happen. Okay, so process in the deadlock state is when every process in the set waiting for event that can be caused only by another process in the set. So this event which actually main concern here and will be acquisition and release. So the types of events may result in the deadlock. Okay, so nanti kita akan tengok example of semaphores, okay, example of process synchronization, okay, di mana akan berlaku deadlock. So another problem with the deadlock adalah apabila berlaku deadlock indefinite blocking, dia akan berlaku juga starvation. Okay, so dia berlaku starvation di mana which process will wait indefinitely within the semaphore. So dia waiting for semaphore tu dia ambil masa yang lama. So that's why dia berlaku starvation. Proses tu nak sangat gunakan nak run the critical section, tapi sebab ada proses lain yang anda pakai yang telah guna, okay, maka dia tidak boleh proses dia punya critical section. So indefinitely the waiting tanpa kesudahan lah. So this is we call a deadlock and also starvation. Apabila berlaku deadlock, maka starvation akan juga berlaku. Alright, so another problem ialah priority inversion. Okay, is a scheduling challenge arise bila they have a higher priority process. So ini juga berlaku apabila kita scheduling pun akan berlaku apabila kita ada hierarchy process need to be read or modify the kernel data that currently being accessed by a lower priority process. So ketika higher priority process nak modify ataupun use the data, okay, yang which actually tengah di-access ataupun sedang digunakan oleh another lower priority process. So a change lower priority process. Since the kernel data are typically protected with the lock, so the higher priority process will have to wait for the lower priority
want to finish with the resources. So this situation become more complicated if the low priority process is preempted in a favor of another process with a higher priority. Okay. Okay. So priority inversion ni lah yang menyebabkan berlaku scheduling punya inconvenience. Okay. One on the system with the tight time constraint, such as real-time systems, the priority inversion can cause a process to take longer than it should to complete dia punya prioritization can cause a problem to take longer than it should be complete task. When it happens, other failures can cascade, resulting the system failure. Okay. So the problems is known as a priority inversion. It occurs when the system with more than two priorities. So one solution is to have only two priorities. That is insufficient for most general purpose operating system. However, typically this system will solve the problem by implementing the priority inheritance protocol. So priority inversion ni akan berlaku lah, okay, di mana bila two system running and they have a priority higher priority process. Okay, so nak solve the problem, kita akan provide priority inheritance protocol, di mana this protocol all process are accessing resources needed by the higher priority process inherit the higher priority until they are finished with the resources in question. So maknanya apa yang dia buat ialah dalam protokol ni, high priority inheritance protocol, kalau proses tu accessing resources with the high priority process, then dia akan inherit, dia akan mewarisi high priority process sampailah dia finish menggunakan resources tersebut lah. Selagi tu dia tak akan kejap higher, kejap lower, tak ada. Okay. So itu antara cara nak solve the problems lah. Okay, so bila dia finish, the priority will revert to the original values. Okay, so bila dia dah finish, the process dah inherit daripada awal sampai akhir, dia buat the process, dia akan continue sampai dia habis, dan dia akan revert balik, dia akan tukar balik kepada original value dia. So bila in the example, priority inheritance protocol will allow process, okay, contohnya dalam proses ni dia kembali process L temporarily inherit the priority of process H. Therefore, they preventing the process M from preempting its execution. When process L had finished using resources R, it will be relinquished inherit priority from the H and assume its original priority. So because R would be able process H not M and not run next. Okay. So ini antaranya yang berlaku lah dalam bila berlaku apabila ada proses lain yang have a different priority. So the high priority process, contoh high priority process adalah contoh high priority process, contohnya process that in the system, in memory systems, okay, operating systems, okay. So dia require high priority process, so dia akan diberi perhatian dululah compared to the lower priority process. So that's why kalau kita tengok macam dalam kita buat scheduling yang sebelum ni kan, even preemptive and non-preemptive scheduling pun dia ada priority, non-preemptive priority scheduling dan juga preemptive priority scheduling. So apa-apa priority will come first. Okay, even other process will come early than the higher priority process. Semaphore, okay. Alright. Do we continue with the next one?